So I want to finish looking at second derivatives. One of the things that is a little bit different than the focus that either honors calculus here or AP calculus has for derivatives is IB really places a lot of emphasis on being able to determine things from the graphs. Like they will give you the graph of a derivative and ask you stuff about the original function, or the graph of the second derivative and ask you stuff about the original function. We'll see this play out a lot as we get to our study on kinematics and other applications, because we're going to see how all these relate, all right? But I just want to reiterate one thing before we get to looking at those graphs here. You can see that we have the set of all the different kinds of stationary points. We have max points, min points, and plateau points. And then we have the set of the points of inflection that we looked at in the previous two lessons here. Okay? We have non-stationary inflections. In other words, these are ones where we're changing concavity, but it's not a critical value. Okay? Then we had the ones that it was at a critical value and we're changing concavity. So that's where we get those plateau points. So this is something I had mentioned in our lesson yesterday, but this intersection right here illustrates basically what we were talking about, where we said all plateau points will be points of inflection, but not all points of inflection will be plateau points. Okay? So I thought this little Venn diagram helped illustrate that point that we were making yesterday. And I just wanted to reiterate that as well. So if you get the derivative equal to 0 and the second derivative equal to 0 at the same point, you automatically are going to know that's a plateau point. That's a point of inflection, and it's a critical value. It's a plateau point. Okay?
So all stationary inflection points or plateau points are also turning points, but not all turning points are plateau.
Well, no, a turning point is either a max or a min point. Okay? A plateau point technically isn't a turning point because we're not changing from increasing to decreasing. That's what we mean by turning.
Okay.
You're changing from increasing to decreasing or decreasing to increasing. So it actually levels off, but it doesn't turn. So that's why it's a plateau. So what I want to do here is actually examine a couple of applications, or a couple of cases here, where we are told what the first derivative is, or actually I should say we're shown what the first derivative is and what the second derivative is. And we want to figure out what the original function is. Okay? So, let's think about this a little bit, and I want to actually use sign diagrams here to help us. Okay? So let's do green, and we got red. Okay, just to keep the colors going here, and we'll do our original function in blue. So let's start first of all by looking at our second derivative. What do you notice about our second derivative?
Straight line.
Okay, it's a straight line.
Constant.
It's constant. What else?
It's 2.
It equals 2. All right.
0.
So it's always going to be
2.
It's always going to be 2, which is a positive number, right?
Yep.
So the entire function is concave up. All right? So look, the second derivative is 2, which is always greater than 0. So the original function is concave up for all real numbers. Okay? So that's one thing that we can tell. Now let's look at our second derivative. Or I'm sorry, our first derivative. Okay? You can see here, we have the first derivative is also linear. Alright? By the way, notice the first derivative has a positive slope. Which makes sense because our acceleration is positive all the time. So it makes sense that our derivative would constantly be increasing. Okay? But you'll notice here, we have this point at 3.50. Okay? What is that?
Critical value.
That's a critical value. Okay? It's a critical value. So, if I were looking at f prime of x, I actually could make a sign diagram, and I would have 3.5 on my sign diagram. Now, to the left of 3.5, my derivative is negative, so I know that my function is
Negative.
decreasing. I know the function is decreasing to the left of 3.5. To the right of 3.5, the derivative is, well, the derivative is positive, so the function is increasing. Alright? So, what do I have at 3.5? It actually is a vertex because what's our function actually going to be? It's a parabola. If we're decreasing and then we're increasing, there's only one change in direction. It's concave up the whole time. Okay, so I know we're going to have a parabola. Now, here's the deal. These right here could be the derivative and second derivative of any parabola that has a vertex where x is 3.5, okay? So my original function might be this, okay? Or my original function might be this, okay? As long as it is on, it has the x coordinate of 3.5 for the vertex, it's that. Here's why that works, guys, okay? All of these are going to have the same derivative and second derivative, but they could be moved up or down because moving up or down is formed by a constant just being added on, okay? So we have this function where the constant could be added on, but when you take the derivative, that constant ends up being 0. It goes away. All right? So we can tell, we can sketch a possible f of x based on this. Okay? Does that make sense? Yeah.
Will we have to find, like, is there a way to find the exact equation?
Not with what we're given. If they said, and it passes through whatever, then we might be able to, okay? But that's actually getting into integration, which we'll do in our next unit. Okay? So, that's kind of an interesting one. We'll look at another example here. Okay, let's zoom in a bit. Okay? So here, our first derivative is a parabola. Our second derivative is a line. Okay, but not a constant this time. Okay, so let's talk about our second derivative. What do you notice?
Negative 5/4 is the critical value.
Okay, negative 5/4 is where our second derivative equals 0. So that means we have a what there? A point of inflection. Okay? Negative 5/4 gives us a point of inflection. Point of inflection. Alright? And our second derivative is what to the left of this? It's negative, which means we are what?
Concave down.
Concave down. Second derivative tells us concavity. Okay? So we could look like, it's going to look like that somewhat to the left of negative 5/4.
So in the last example, it was positive, and that's how we could tell it was concave upwards.
It was always positive. That's why it was always going to be concave up.
What's the right after the error? Like E?
Oh, point of inflection. Sorry, I was just abbreviating. Point of inflection. Okay. To the right of negative 5/4, our second derivative is positive, which means we are concave up. All right? So, remember, concave down looks like a frown, concave up looks like a cup. All right? It's an easy way to remember it. Okay. So, we've got our second derivative, and now we know a little bit about our original function already. So let's look at the first derivative. Okay? What do you see with our first derivative?
It's a parabola.
It is a parabola.
It's got zeros at negative 3.5.
Good. They're critical values, which are zeros at negative 3.5. So by the way, when you're constructing sign diagrams, I like to do them side by side, like this. And I also will put the points kind of relative to each other. So negative 3 is going to be to the left of negative 5/4. And positive 1/2 is going to be like over here. Okay, you'll see why we do this later too when we get to the applications more. Okay, so what do we know about the derivative, the first derivative to the left of negative 3? Well, the derivative is decreasing, but the derivative is positive. Okay? The derivative is positive. Because here's the thing, it continues to decrease until we get to that point of inflection. Okay? But when we're looking at the first derivative, we want to say positive or negative, and that means, since it's positive, it means the original function is increasing until we get to negative 3. Okay? Between negative 3.5, our derivative is negative. So our function is decreasing. Okay?
And then again, increasing after.
Good. Now it's positive again, so we're increasing again. So what is the graph of what is the original function actually going to be in this case? It's a cubic, yeah. All right. So as I'm graphing this, and again, it could be shifted up or down vertically. We don't know exactly where it is vertically, but we can get the general shape. Here's going to be a point of inflection. At negative 3, what are we going to have?
It's a maximum.
Turning point.
It's a maximum point. It's a turning point. It's more specifically a max point.
The same way as 1/2?
Well, at 1/2, what do we have?
Minimum.
Minimum.
It's a minimum point, okay? So let's say that it happened to be here. So notice here, I'm increasing, but I'm concave down, right? And I continue to be concave down even though I'm decreasing now. Then I pass my point of inflection. At this moment, I've started to be concave up, but I'm still decreasing. Okay? That is right here. I'm concave up, but I'm still decreasing. All right? This is why I like to put these side by side. I was increasing but concave down. Then I started decreasing, but I was still concave down. Now I'm concave up, but I'm still decreasing. Then when I hit here,
Concave up.
I start to increase, and it's continuing to be concave up. All right, so there we have it.
So what were the derivatives of a function like sine or cosine look like the first and second derivatives?
Well, the derivative of sine is cosine, right?
Mm-hmm.
So a
And then
sine
another-
curve, the derivative of a sine curve is a cosine curve. Okay? So yeah, like over here we have the sine curve drawn. The derivative would just be that.
And then the second derivative?
The second derivative would be negative
Negative.
sine, so it would be this.
Huh, okay. So then you'd be able to tell almost immediately, basically, that that's a sine or a cosine.
Yeah, yeah, yeah. Yes.
So I'm kind of confused, when you're drawing your sine graph for the for f prime, I'm like why was like -3 a maximum?
-3 was a maximum because, well, we could have shown it two ways. We knew it's a critical value because our first derivative is 0.
Yeah.
But then here's where the two different ways come in. We could also see, we know it's a max because the second derivative is negative. That means we're concave down. If you're concave down at a critical value, it's automatically a max. That was our second derivative test we looked at yesterday. Okay? The way we learned earlier, when all we had was the first derivative, was look for a change in direction. Okay? We're increasing before, we're decreasing after, that means it's a max point. Okay? Over here we know a half is a min because we were decreasing, then we went to increasing, or because we knew that we were concave up at 1/2. So again, either one of those would prove what those are. Okay? Alright, more. I want you guys to take a couple minutes here and try to sketch this one on your own, and then we'll go over this, okay? Alright, who wants to share their work with us?
Yeah, no,
Brian
it's
does.
Who wants to share their work with us?
I definitely will volunteer Brian to show his work. Oh, nominate.
Alright, show me what you got. If you volunteer someone else, you just volunteered.
Oh, no, I would like
Where's your work?
Oh, I was about to get.
Alright, so let's look at what Ben came up with here.
Ben, what did you do?
What did I do?
We've got sign diagrams first of all. And notice both of these had critical values or had zeros at 1. Alright, so we saw that the second derivative was positive to the left of 1 and negative to the right of 1. So it's concave up to the left and concave down to the right. Okay? So there's the first thing. Then with our first derivative, it also had a 0 at 1, but it was negative. It was below the x-axis on both sides. So we're decreasing. The original function is decreasing, and then it continues to decrease. When you do not have a change in sign on your first derivative, what does it mean?
Plateau point.
It's a plateau point, okay? So, as you can see here, Ben made it actually hit the point 10, but notice here we're decreasing, but it's concave up. Alright, you can see if we kept drawing it with that same concavity, it would start going up. There's the concave up side. But at this point, we continue to decrease, but now it's arching down. It's concave down. Okay? Now, the reality is, I think everybody that showed me one had it hitting that point 10, and why not? Everything else hits 10. But the fact of the matter is, as long as that plateau point is somewhere where x equals 1, our graph could be this, okay? With a plateau point there. Or it could be down here, okay? It doesn't matter. All of those are possibilities for the information we've been given, okay?
I got 96.45% of that.
I'm just confused with the f prime of x.
Which is
Why is it to the left of the 1, why is it negative?
Well, cause it's below the x-axis.
So because both sides are left, both sides are underneath the x-axis, they're both going to be negative.
Yes.
If the left side was above the x-axis, and like looked like our new line, it looked like our f of x, for example,
Uh-huh.
then it would be positive,
Mm-hmm.
then the 1, the critical value, and then negative.
Yeah.
Oh, word. Okay.
Mm-hmm.
So I was right.
Yeah, you were absolutely right.
Never doubted.
Okay. Never doubted it for a second. I didn't.
I doubted myself.
So. Alright, so that's it as far as the second derivative, okay? Finding the second derivatives, applying it in a basic sense here. We're gonna look more at applying it in specific cases as we move forward. Particularly when we get to the kinematics and the optimization and that sort of thing, okay? So,